let's start with the introduction to the synthesis. Okay. So first, let's see the meaning of synthesis. Synthesis is like converting. Okay. Like in the word photosynthesis, you remember it converts the trees converts photons, that is the sunlight, into energy. Likewise, in the world of synthesis, or we can say VLSI, synthesis is the process of converting or translating RTL code. It is a high level RTL code into gate level netlist. Okay, so let's, uh, yeah. So what is synthesis? As I said, synthesis is the process of translating or converting RTL code, high level RTL code, into gate level netlist. So we can also express synthesis as translation plus optimization plus mapping. Okay. Translation is nothing but we are converting RTL into gate level netlist, right? It is the tool is doing the uh, translation. Okay. The tool also needs to do the optimization using constraints. Okay, to meet power, performance, and area, and also mapping. Mapping is like binding the optimized netlist to physical cells from a technology file. Okay. So we can say synthesis is translation plus optimization plus mapping. So we have learned what is synthesis till now. And now let's go to the next topic, which is why synthesis is important. Okay. Okay. Before that, let's see what are the types of synthesis. There are two types of synthesis. One is the logical synthesis and the other one is physical synthesis. Okay. So logical synthesis is converting RTL into gate level netlist, and physical synthesis is it takes the gate level netlist and maps it to the specified IC. Okay, you need to understand the difference between logical synthesis and physical synthesis. Okay, so now let's move further. So let's see the importance of synthesis in VLSI flow. So as we know, synthesis is the process of translating high level RTL code into gate level netlist. So the importance is that it is a critical step which bridges the gap between logical design and physical implementation. Okay, you need to be you need to know what is the importance of synthesis in VLSI flow. It is that it's a critical step which bridges the gap between logical design and physical implementation. Okay, so now let's see the importance of gate level netlist. Of course, we are converting into gate level netlist, but we need to know what is gate level netlist. Okay, so gate level netlist is it provides a detailed gate level representation of the design, which enables the accurate physical implementation, verification, and optimization for area, power, and timing. Okay, so this is the reason why gate level netlist, which is the output of the synthesis, is given to the PD team. So what is the input of the PD team here? The gate level netlist. Okay, so let's move to the next topic. So let's now see what are the inputs of the synthesis. I hope I'm not going too fast and you're understanding the topics pretty well, right? Uh, So now let's see what are the inputs of the synthesis. I think everyone is muted. That's the reason why no one is asking me a question. I was waiting if someone will ask any questions. So let's see the chat. Okay, sure. Okay, little slow. Okay, no problem. I'll just try to be little slower. The thing is, you can't see what I'm saying, the sentences in the PPT, right? So you just you can write it, whatever I'm saying, no? You just write it on a book. If you want, I can repeat it once again. Do you want me to repeat the like sentences so that you can write in a good English sentences for the future uses? Okay, let me give you the sentences, okay? If someone asks you, what is synthesis? You just need to say, synthesis is the process of translating, or you can say converting the high level RTL code into gate level netlist. Okay. And when someone asks you the importance of gate level netlist, you can say it is the detailed gate level representation of the design. Okay, sure, no problem. So now let's go to the next topic, that is the inputs of the synthesis. Of course, as I said, RTL gets converted into gate level netlist. So of course, there is a RTL file, which is the input of the synthesis. So like .v format or VHDL format, okay? We can now say you need to know the importance of RTL, that is register transfer level. It is written in Verilog or VHDL file. It describes the behavior of the digital circuit in terms of registers, data flow, and operation. Okay, so you can say the RTL describes the behavior of digital circuit. The next input is technology libraries. Those are .lib file, .lef file, or .tf file. Okay, .tf file is technology file, .lef is library exchange format, and lib file is timing library, or we can say liberty file. Okay, so the .lib file contains cell delays, transition, setup, and hold time requirements. Okay, it contains cell delays, transition, setup, and hold time requirements. So this .lib file can be generated using CCS technique or NLDM technique. CCS technique is composite current source, and NLDM is non-linear delay model. Okay. So coming to the .lef file, that is library exchange format. So it has the contents like place and route boundary, pin position, metal layer information, etc. So coming to the technology file, it contains the physical properties of fabrication process. It contains the information like resistance, capacitance, design rules, width, spacing. So technology file is compatible both with both .lib as well as .lef file. Coming to the next input, that is constraints. Constraints or .sdc file. .sdc, the full form is synopsis design constraints. So, first, before that, let's discuss what are constraints. Okay. Constraints are the limits or the rules which you impose on the design via tools like DC shell to get your desired outcome or output, we can say. Let me give you a general example. For example, you're going to the gym. Your desired outcome is having a fit body as well as a healthy mind. Okay. So likewise, uh, so you will constrain yourself to stay on a strict diet plan as well as on a strict workout plan. So you're constraining yourself. That's the meaning of constraint here. Okay. I'll repeat it once again. Constraints are the limits or the rules which you impose on the design via tools like DC shell to get your desired outcome. Okay. Your desired output. So SDCs contains clock details, input output delays, DRCs. Those are the design rule constraints and clock exceptions. So I'll give you the commands later because we need to be industry ready. Yeah, we are gaining the industry ready skills. So of course you need to know the commands. I'll tell you those later. Now let's completely see the uh, all logical things and theoretical things for now. Okay. Uh, Constraint files. Okay, now let's see the examples of the constraint.sdc file. Those are create clock, create generated clock, set set clock latency, set clock uncertainty, set max area. These are the examples of constraints. Okay, coming to the next file, that is the UPF file, or you can say United Power Unified Power Format. Okay, so power format, it is a standardized file format used to describe power intent in IC designs. Okay, it's a standardized file format used to describe power intent in IC design. It specifies how power is managed across different parts of a design. Okay, enabling low power techniques like power gating, cell isolation technique, power aware automation, etc. Okay, that is the importance of unified power format, that is the UPF file. So coming to the outputs of the synthesis. So uh, can anyone say, I'll see the chat, can anyone say what are the outputs you can expect from the synthesis? I already said you the uh, about the meaning of the synthesis and this how you can express it. Can anyone tell me what are the outputs of the synthesis? Yeah, netlist, gate level netlist. Yeah, yeah, and even SDC file. Yeah, good, good. So now let's discuss about those. Okay. Yeah, UPF file as well. So let's see the outputs of the synthesis. So if the interviewer asks you, so what are the outputs of the synthesis and inputs of the synthesis? You can just say the things I'm mentioning here. Okay. Of course, the gate level netlist, the SDC file, the UPF, and also the reports. Okay. Because when we try to solve the timing violation and stuff, we of course need to check the reports. Okay. Like report timing, report QOR. I'm giving you the examples of reports. Okay. How you need to see the reports. Okay, so we have learned what is synthesis, importance of synthesis, gate level netlist, inputs and outputs of the synthesis. So now let's see the next topic. Yeah, before that, you can see here the examples of netlist. Okay, example of netlist and example of RTL. Here you can see that it is represented like this using gates, and here you can represent it like this. Okay. This is the example of RTL and example of netlist. This is the example of .lib file. Okay, you can see here. And this is the example of .tf file. See, you can see TSMC 28 nanometer like that. Technology file is described like this. So this is the example of SDC file. As I gave you the examples, right? Create clock, set input delay, set output delay, set max area. These are the examples of SDC. So now let's see the goals of the synthesis. Of course, we need to have a goal in our mind before starting the synthesis, right? These are the goals we need to achieve. The first one is to generate a gate level netlist. Of course, our main goal is generating gate level netlist, which can be served as an input to the physical design tool. Okay. Next, the second goal is insertion of clock gating techniques. So I think you already know the clock gating technique, right? It is a technique which is used to save the power. Okay. So whenever our circuit is at use, only then the clock signal is given to that circuit. Till then it is off, it is not given, which saves a lot of power. Okay, our power get optimized due to clock gating technique. So now after this, our other goal is logical optimization. Okay, we need to reduce the area, of course, the power consumption. Okay, so this can be done using the compile command. I'll get to that later. Okay. uh, and also using constraints, we can optimize it. So coming to the other goal, that is inserting DFT logic. Okay, so now let's discuss what is DFT. DFT full form is designed for testability. Okay, remember it, DFT, designed for testability. It is a method where we can check for failures in the functionality due to manufacturing faults by inserting test pattern generations in the design. Okay, by inserting test pattern generation, we can check for the failures in the functionality due to manufacturing faults. You can write it down if you wanted to. Okay. Uh, the meaning of BIST is built-in self-test. Okay, built-in self-test. After this, our last goal will be that there should be no logical equivalent change between RTL and gate level netlist, which means the logical equivalence between RTL and gate level netlist should be maintained. After all the synthesis, we'll do the simple LEC checks. You know what LEC check is? It is logical equivalence check. So the purpose is to formally verify that the synthesized gate netlist is functionally identical to the original RTL code. Because what happens, sometimes the synthesis tool can unintentionally alter the design's logic while optimizing it. It is unintentional, okay? But sometimes it can happen. So we cannot take any risk. That's why we do LEC checks. So I'll repeat it once again. The purpose of LEC check is to formally verify that the synthesized gate netlist is functionally identical to the original RTL code. Okay, so these are the goals of the synthesis. So now we have even covered goals of the synthesis. Let's go to the next topic, like constraint. I have explained you giving a best example what constraints are. Now let's discuss. There are two types of constraints, like design rule constraints and optimization constraints. Of course, design rule constraints are max transition, max capacitance, and max fan out. So even one of this has a violation, our whole design will fail. So there should be no design rule violations. Okay. So the logic library defines this implicit constraint. These constraints are required for a design to function correctly. So even one of the design rule constraint fails or has violations in it, our design will not work correctly. Okay. They apply to any design that uses the library by default. By default, design rule constraints have a higher priority than optimization constraints. So what can be the optimization constraint? I gave you the examples already. Those are like create clock, set max area, so on. Okay, those are the examples of optimization constraints. So I think you have understood what constraints are, and there are two types of constraints: design rule constraints as well as optimization constraints. Now let's dive into the main and the what you call the everything of the synthesis. It is the flow of the synthesis. Okay. Now here I'll be giving you the examples of commands also while we are using the TC shell. So please note it down, okay, without any errors or something, because the command should not change. It should be as it is. So the first step is developing HDL files. We get this HDL file. It is the RTL file. Oh, sorry, RTL file from the RTL team. Okay, they develop the HDL file. HDL full form. Can anyone tell me the full form of HDL? No, no, no. Yeah, it's hardware description language. Okay, hardware description language. Yeah, all of you, most of the people got right. Yeah, so this will be in .v or VHDL format, as I said earlier. After that, we need to specify libraries. Okay, while specifying the libraries, we need to load the libraries into the database. So we can use the commands like set space link library. And in the flower brackets, you can write the path. You can give the path of the file. It is a DB file in DC shell, okay? And set space target library. So let me tell you a small difference between set link library and set target library, okay? So link library specify libraries which are used to resolve references, okay? And target library defines the library used to map the design to the standard cells during synthesis. Okay, and other two also the examples to load the file in libraries into the database. You can write it down. I think you can see it clearly, right? If you don't say it clearly, I can uh, tell you. Okay, I'll just tell the spelling. Okay, so now we have loaded our library files. After that, we need to read our design. We can read the design using, okay, link library. Okay, link library. It specifies libraries which are used to resolve references. Okay, this is the definition of link library. So where was I? Yeah, I was reading the design, right? So there are commands like analyze and elaborate. So let me explain you what the command analyze do. Okay, analyze checks for the syntax errors. Okay, we are loading the files, right? Library into the database, right? So it checks for the syntax error in our code, or you can say design, and it creates a HDL library objects in an intermediate form. That's what the analyze command do. Elaborate command. Now let's see the elaborate command. it translates the design into GTEC format. GTEC format is like a generic technology format, okay? Which is a technology independent gate level netlist, okay? It allows changing of parameter values defined in the source code. We can also, the elaborate command also replaces HDL arithmetic operators in the code with design where components. So I will define you what is design where components. Okay, design where components are already pre-optimized for PPA purposes. Okay, for power, performance, and area, these are already pre-optimized. So it replaces HDL arithmetic operators in the code with design where components. That is the definition of elaboration. So we have developed the HDL file. We have loaded the libraries into the database, and now we have read the design. So, okay, let me give you the command read file. Okay, the command read file does the analyze and elaboration together. Okay, that is the read file command. Okay, now let's see the next step, that is the define design environment. Okay, so while we are defining design environment, it contains operating conditions, wire load models, and system interface requirements. Okay, now let's see what are operating conditions. Operating conditions, it consists of process, voltage, and temperature, PVT conditions. You remember it, right? PVT conditions. So the effects of these on chip should be considered during synthesis. And let's go to the wire load models. It allows DC to estimate the effect of wire length and fan out on resistance, capacitance, and area of nets. I'll repeat it once again. It allows DC, our tool, to estimate the effect of wire length and fan out on resistance, capacitance, and area of nets. So now let's go to system interface. System interface, like the example set driving cell. This is a command, example command, set load, set output fan out load. These are the example commands. So the information regarding outside logic driving and receiving signals from your ASIC is captured through these constants. Okay, let me explain you once again, the information regarding outside logic driving and receiving signals from your ASIC is captured through these constants. Like these constants are set driving cell, set load, set output fan out load, okay, set fan out load, etc. So after this, the next step is defining constraints, okay, specifying constraints. Of course, you know, I have explained you the constraint. Those are DRCs and optimization constraint. These are the examples. Set set max transition, set max fan out, set max capacitance are the design rule constants. Create clock latency, create clock uncertainty, set max area, set output delay, set input delay. These are the optimization constraints. So after specifying the constraints, we need to go to the next step, that is select compile strategy. Now let's see the compile strategies. Okay, there are three types of strategies, compiling strategies. Those are top down, bottom up, and mixed. You can write this down, okay? Or because writing is simpler. Instead of saying the whole recorded session, you can just write it down. So what does the top down compilation strategy do? So here the top level design and all its sub design are compiled together, okay? The top level design and all its sub designs are compiled together. So now let's see bottom up compilation. It's just the reverse version, means here it's compiled together, right? But here the sub designs are compiled separately, starting from the bottom of the hierarchy and proceeding up through the levels of the hierarchy until the top level design is compiled. Okay, I repeat it once again. The individual sub-designs are compiled separately. Okay, unlike top-down compilation, bottom-up compilation, the individual sub-designs are compiled separately, starting from the bottom of the hierarchy and proceeding up through the levels of the hierarchy until the top level design is compiled. Okay, so mixed is the both top down or bottom up, whichever is more appropriate gets applied to the individual design. Okay, so these are the compiled strategies. So after the compiled strategies, we need to choose. We need to choose that whether we are going to use top down, bottom up, or mixed. Then we need to optimize our design. So optimizing the design, I told you the command is compile or compile ultra. So now let's see what is compile. The process of optimization is done through the command called compile ultra. Okay. Optimization consists of three steps: architectural, logical, gate level. Architectural. Now let's see what is architectural. Okay. Like this is an optimization after which the design is represented in GTEC format. You know the GTEC format, generic technology format. Okay. So in logic level, it can be described as Boolean equation manipulation. Okay. It can be subdivided into two processes, that is structuring and flattening. Let's see it later. So you just need to remember logic level, Boolean equation manipulation. So the gate level. Now let's see the gate level. It is during this stage, the logic is actually converted into gates. This optimization then has four processes, that is mapping, delay optimization, design rule fixing, and area optimization. Okay, this is what compile is. Okay, you can use compile ultra command in or compile command for the optimization of the design. You can repeat it n number of times until you get no timing violations and like your desired outcome. Okay. So after this, you need to generate reports. Yeah, of course, you need to see the reports, right? If the if there are any timing violations, all the timing requirements are met or not. So you need to analyze and resolve design problems. You can use uh, the commands like report timing, report QOR, report constraint, report clock timing. These are the commands which I'm saying you. Okay, these are important commands. So report QOR, by this command, you can check the quality of your design, like uh, DRVs, static power, and compile time details in this report. Okay, report QOR. In report timing, it gives the detail pin point to point information. Okay, pinpoint information on clock paths, data paths that have worst slack along with delays and slack calculation. Let's discuss about this slack later. Okay. You know the data paths, right? The group pathing technique where that is the input to register, register to register, register to output, and input to output. I think this is common. Most of the people know. So this is the okay. After this, of course, we need to save the design also. Till here, you will try to fix any violations and also optimize PPS, that is power, performance, and area. After this, you need to save your design. For saving your design, you can use the write command, WRITE, write command. Okay, with hyphen format. I'm telling you the syntax, right? Hyphen format. If it's a Verilog, you can just type Verilog, then hyphen hierarchy, hyphen output, and you can give a name. Okay, this is the syntax of write command. You can save your design. So by this, we have covered what is synthesis, the importance of synthesis in VLSI flow, gate level netlist, inputs of synthesis, outputs of synthesis, goals of the synthesis, and synthesis flow. Like it's not a complete detailed flow, but you have got an idea. Okay, with commands of DC shell, because I'm here to explain about the DC shell. That's why. Okay, so I think till here you have understand most of the topics. Now let's see if you have any doubts or something. If actually there are many more topics like Slack, what is required time, arrival time, setup and holds. You need to know what are HVTs and LVTs. What happens if there's a setup violation? Means it goes into a metastable state, right? So what happens if there's a setup violation or hold violation? And how you can fix those setup and hold violation. That is very important. And basic topics like what is jitter, what is latency, what is duty cycle, and most of the people gets confused between skew and slew because it's almost similar, right? So most of the people get confused between skew and slew. Slew is like a transition time, the switching between from 0 to 1 or 1 to 0. Okay, that is slew. And skew is the difference between arrival times between two different flops or registers, you can say. Okay. And then there are different optimization techniques like group pathing technique, ungrouping, and boundary optimization technique, etc. Of course, because we are optimizing, our main goal is to optimize the design as well, right? Getting the gate level netlist as well as optimizing and generating reports and saving the design. I'll We can discuss it further. Okay. So thank you. If you have any doubts, you can ask me. I think I have completed pretty quickly. If you want, I can explain once again. Suppose on doubts in chat. Yeah, I can recap. Yeah. Okay. I'll just solve the first doubt, which is the difference between logical synthesis and physical synthesis. Okay. I'll just give you the definition. So logical synthesis is translating RTL, high level RTL code into gate level netlist. Okay. You got what is logical synthesis, right? And coming to the physical synthesis, the same gate level netlist you got from the logical synthesis, right? It gets mapped to the specified IC. IC is like integrated circuit. It gets mapped. Okay. I told you, right, the importance of synthesis. What is importance of synthesis in VLSI flow? Like it bridges the gap between logical design and physical implementation. You got it right. Likewise. So now let's go to the next doubt. Okay, so CCS and NLDM, right? So I'll explain you what is CCS. It is composite current source. Okay, you can write it down. It is composite current source. And NLDM is non-linear delay model. You can write it down. Non-linear delay models. I'll just tell you the small difference between them. Actually, these are the techniques used to generate .lib file, that is the Liberty files. And the CCS contains 20 variables. So, and NLDM contains only 2 variables. So CCS is 10 times more in size compared to the NLDM. But the thing is, it is detailed and accurate and has more the disadvantage is it has more runtime. Whereas NLDM, it is 10 times less in size than CCS. So it is less accurate, of course, but the runtime is also less. It is the advantage. So let's see the next one. Can you say top to bottom? Okay, it's top down or bottom up strategies. Okay, I think you're asking me the Manish Kant. Okay, you're asking me the strategies, right? Top down or bottom up strategies. Difference between compile and compile ultra. Yeah, those are the commands actually. Nothing much, but compile ultra is like it will try to optimize it more. That's it. If your design gets satisfied with no violations and a good optimized PPA just by using the compile command, it's well and good. Or else you can use the compile ultra command. Specify from percent. Yeah, we'll get from the front end team. The UPF file also will be getting from the front end team as well. Logic translation mapping and optimization. Okay, you need means I told you, right? Synthesis is translation, Kumar. Synthesis is translation plus mapping plus optimization, right? Let me show you the PPT. See, synthesis, translation plus optimization plus mapping. So translation is like translating RTL into gate level netlist. Optimizing like using constraints, like I have given you the examples of the constraints like set max area, set clock uncertainty. Okay, those are the examples of constraint. Using those constraints, we need to try to meet the power, performance, and area. Okay, this is how we can do the optimization. So we have completed translation and optimization. Now let's see the mapping. Mapping is like basically binding the optimized netlist to physical cells from technology file, .tf files, okay, .lib files. Yeah, it's like basically mapping. What happens in elaborate? Okay, so Kumar, in elaborate, as I told you already, like in analyze, it reads the design and checks for the syntax error, right? In elaborate, it translates the design into GTEC format and it replaces HDL arithmetic operators in the code with design where components. Okay, design where components are pre-optimized for PPA purposes. Okay, so that's what happens in the elaboration. Yeah, and also it allows changing of parameter values defined in the source code. There's a source code, right? It allows changing of parameter values. This is what happens in elaboration. Can we use the CCS? Of course, we can. When we can use CCS, we'll be getting this from the other teams like as an input. Uh, Basically, CCS is like detailed version, accurate version. So it depends on our project which we are doing. The PPT from the starting because you joined. Okay, okay. Yeah, those variables. I do need to check what are the 20 parameters. Yeah. Okay. Yeah, it's like pre-floor plan. It's not like we need to do. We need to like optimize it before floor planning, power planning, etc. Okay, so that the PD team should not be getting much complications in the future. While I'm trying for physical synthesis, right? Yeah, you can say that, but compile and compile ultra are like just similar only. Nothing much of a difference in that. Physical something. Okay, do you know about scan buffer cells? Yeah, of course, you know scan insertion. Like for DFT also you do scan insertion. It's like basically connecting the output of one flip-flop to its sequential flip-flops. So the output of one flip-flop will be given to the input of the other flip-flop, and it forms a chain. And we just need to compare that the output which we are getting is like the expected output or not. Physical synthesis will take place. Grouping path. Okay, so let me explain you the optimization techniques like group pathing method, path grouping method, we can say, because the command is group path. So I'll explain you it. Uh, so optimization techniques, you know the group paths, right? Path groups, those are the input to register, register to register, register to output, and input to output, right? So these are the, so it like basically separates input output paths, like it isolates input outputs path so that you can compile, you can get better compiling results. Okay. So let's see what is boundary optimization. Okay, this is an optimization technique. It involves adjusting the position of cells or modules to minimize the distance between connected components and reduce wire length. Okay, this is what you call boundary optimization. This technique aims to reduce wire length and capacitance, improve signal integrity and timing, increase routing efficiency, and decrease power consumption. Okay, this is the boundary optimization. I'll repeat it once again. Boundary optimization, it involves adjusting the position of cells or modules to minimize the distance between connected components and reduce the wire length. So this technique aims to reduce wire length, of course, and also the capacitance, improve signal integrity and timing, increase routing efficiency, and decrease power consumption. So let's go to the other optimization technique, which is ungrouping. So ungrouping is basically will merge the subdesigns of a given level into one parent cell or a design, you can say. It removes hierarchical boundaries and allows the levels of the logic and to improve area by sharing logic. Okay. So it basically merges subdesigns into a parent cell. It removes hierarchical boundaries and allows our compiler, DC compiler, to improve timing by reducing the levels of logic and to improve area. Copy Desi Kumar. So logical synthesis is basically translating RTL into gate level netlist. But the importance of synthesis is bridging a gap between logical design and physical implementation, right? So if there's a gate level netlist, right? So it's completely using gates. It is completely represented using gates. So it will be easier for the physical implementation. Okay. That's why in physical implementation, we are mapping. It takes the gate level netlist and maps it to the specific or specified IC, integrated circuits. Gate level compilation. Yeah, compiling, it's a command. Here, I told you architectural level, logic level, and gate level. So I need to, should I explain you the gate level compilation once again? Okay, I'll explain you the gate level compilation. So here in gate level compilation, it's like the first you need to understand what is compiling. It is the process of optimization. Okay. We use the commands like compile or compile ultra. So it has three steps, that is architectural, logical level, and gate level. Okay. In architectural level, it optimizes in such a way that the design can be the design next is represented in GTEC format. Okay. In logical level, we need to remember that it is a Boolean equation manipulation. And gate level compilation, actually it is during this stage, our tool gets actually, the tool converts the logic into gates. So it has mapping, delay optimization, design rule fixing, and optimization. See, I'll show you in the gate level. It is during this the logic is actually converted into gates. This optimization has four processes: mapping, delay optimization, design rule fixing, and area optimization. Okay, this happens in the gate level. Okay, so Gopi Desikumar, you got a doubt that RTL as a .v. Okay, very log file. And after synthesis also, we are getting a .v file because, okay, so uh, you need to know the difference. Here, the .v, I'll show you the examples here. You can see the examples between examples of RTL and gate level netlist. You need to know this is like uh, Verilog code only, but it is completely defined using gates here. You can see here, right? And gate is used, or mux is kind of, because mux is also a collection of gates, right? So like that it is represented. But here you use always commands. You know the RTL flow, right? The four levels. We can represent it in any of those. But here it is only represented using gates. So that is the difference between RTL and netlist. Got it now? Gopi Desi Kumar? No, you didn't get it. Both are in .v format only, and it can be used as the input to the PD team. Sorry if I cannot solve few of the doubts. The doubts I cannot say right now. I'll just look into it and contact you later. Okay. Modes of wire load model. Yeah, I'll explain you the wire load model now. So as we know, it is like when we are defining design environment, we need to check for the operating conditions, wire load models, and system interface requirements. Okay, we need to check those. So in wire load models, so we basically allows DC, our tool, to estimate the effect of wire length and fan out on resistance, capacitance, and area of nets. Okay, I'll repeat it once again. Wire load models. It allows DC, a tool, to estimate the effects of wire length and fan out on resistance, capacitance, and area of nets. This is written Verilog code of netlist and RTL. Brinkley Babu. So let me tell you the difference between RTL and gate level netlist. Of course, we can represent it in the RTL also. We can see the gate level modeling as well. You can say that it is same, but the thing is here it is the optimized version. After synthesizing, after synthesis, we get a netlist, right? It is the optimized netlist. And of course, both are represented in .v format only. GTEx cells, I need to see it, okay? I just couldn't recall it, but I'll see it for sure. Go into one mask, or if switch case is there, then it converts to any product. Like this, yeah. There's something like that only, because here there is no if else statements or like that. Everything is represented only using age something. Anything else? I just gave you these examples. We'll be discussing more of the examples. You'll get the clear idea. Okay. This is just my demo class, right? So I thought I'll just give you, give you all the quick glimpse of all this. Yeah. Thank you, Shivakumar, for explaining what are GTEx cell. Thank you. I too got to know. I just recalled it now. Contains both combinational and sequential cells. Cells formed in elaborate stages in synthesis. Okay. Thanks a lot, Shivakumar. Okay, I gave you a clip, a quick glimpse on all the topics of the synthesis, right? You got it. We can further discuss the setup and hold things, violations, and how to fix them. HVT and LVT cells. What are those? What are the importance of HVTs and LVT cells? And like when you need to add those or when you need to remove those for better performance and so on. We can discuss it later. Okay. We give to the DFT team for testing our design actually. After that, we'll, if it's okay, then we'll move forward, or else we need to check once again. I think you're satisfied with my explanation. Sorry for moving so fast in the starting stages. Then I think I have uh, like come into a rhythm so that you can understand what I was explaining. Okay. Thank you all.
Anyone have any doubt now? So if you don't have any doubt, you can just write you can just WhatsApp us if you have any doubt regarding courses, right? I'm dropping my WhatsApp number. If you have any doubt regarding course details and anything, uh, so synthesis part will be covered by another faculty. Okay, then thank you so much, everyone. Thank you. Thank you, sir. Thank you.